The 12th century in Europe witnessed a resurgence of interest in ancient knowledge. This period marked a significant turning point in the intellectual history of the continent. Scholars rediscovered Greek and Arabic texts that had been lost or forgotten for centuries. These texts were not just simple manuscripts, they were treasure troves of wisdom and knowledge that had been buried by the sands of time. These texts, translated into Latin, revealed the mathematical brilliance of ancient civilizations. The process of translation itself was a monumental task, requiring immense dedication and scholarly rigor. They contained works by Euclid, Archimedes, and other Greek masters, as well as the groundbreaking mathematics developed by Islamic scholars. The contributions of these scholars were instrumental in shaping the mathematical landscape of the time. This influx of knowledge sparked a revival of mathematics in Europe. It was a period of intense intellectual activity, where scholars eagerly absorbed and built upon the ancient wisdom. Universities played a crucial role in this revival. These institutions became the epicenters of learning, attracting scholars from all corners of Europe. They became centers of learning where scholars from different countries gathered to study and debate. The exchange of ideas in these academic settings was vital for the advancement of knowledge. The rediscovery of ancient mathematical texts provided a foundation for new discoveries. Scholars meticulously analyzed these texts, seeking to understand and expand upon the ideas they contained. Mathematicians began to build upon the work of their predecessors, pushing the boundaries of knowledge further than ever before. This era saw the birth of new mathematical theories and concepts that would shape the future. This period also saw the emergence of practical mathematics. The application of mathematical principles in everyday life became increasingly important. Merchants and traders needed efficient ways to calculate profits and losses. The development of practical mathematical tools and techniques was essential for the growth of commerce. Navigators required accurate methods for determining their position at sea. The advancements in mathematical knowledge were crucial for the progress of navigation and exploration. These practical demands further fueled the growth of mathematics during this era. The need for precise calculations in trade and navigation drove innovation and the development of new mathematical methods. The revival of mathematics was not merely a rediscovery of old ideas. It was a dynamic process of assimilation, innovation, and application that transformed the intellectual landscape of Europe. It was a dynamic process of assimilation, innovation, and application that laid the groundwork for the scientific revolution to come. The mathematical advancements of this period were a crucial stepping stone towards the modern scientific era, influencing countless fields and disciplines. One of the most significant developments during this period was the introduction of Hindu-Arabic numerals to Europe. This transformative event marked a pivotal moment in the history of mathematics and science. These numerals, with their 10 digits and the concept of zero, offered a far more efficient system for writing and manipulating numbers than the cumbersome Roman numerals. The simplicity and elegance of the Hindu-Arabic system made it easier to perform arithmetic operations, which was a game-changer for scholars and merchants alike. This innovation, originating in India and transmitted to Europe through Arab mathematicians, revolutionized mathematics. The journey of these numerals from the Indian subcontinent through the Islamic world and finally to Europe is a testament to the interconnectedness of human knowledge and the collaborative nature of scientific progress. Prior to the adoption of Hindu-Arabic numerals, calculations were often performed using an abacus or counting boards. These tools, while useful, had significant limitations. These methods were slow and prone to errors. The manual nature of these tools meant that even simple calculations could be time-consuming and error-prone, hindering the efficiency of trade and scientific inquiry. The new numerals allowed for faster and more accurate calculations. This newfound efficiency was not just a minor improvement, it was a revolutionary change that enabled more complex and sophisticated mathematical work. This had a profound impact on various fields, from commerce and trade to astronomy and engineering. Merchants could keep more accurate records, astronomers could make more precise calculations, and engineers could design more complex structures. The transition from Roman numerals to Hindu-Arabic numerals was not without its challenges. Educational institutions had to overhaul their curricula, and scholars had to relearn basic arithmetic. Some resisted the new system, clinging to the familiar methods of the past. This resistance was rooted in tradition and the natural human tendency to resist change. However, the advantages of the Hindu-Arabic system were undeniable. Its ease of use and versatility quickly won over even the most skeptical of scholars. Its simplicity and versatility made it an indispensable tool for mathematicians, scientists, and anyone working with numbers. The ability to perform complex calculations with relative ease opened up new possibilities in various scientific fields. The adoption of Hindu-Arabic numerals paved the way for significant advancements in mathematics. It laid the groundwork for the development of algebra, calculus, and other advanced mathematical disciplines. It simplified mathematical notation, making it easier to express complex ideas. This simplification was crucial for the communication and dissemination of new mathematical theories. This in turn fostered new discoveries and accelerated the pace of mathematical progress. The ripple effects of this innovation can still be felt today, as modern mathematics continues to build on the foundation laid by the adoption of Hindu-Arabic numerals.
Leonardo of Pisa, better known as Fibonacci, was one of the most influential mathematicians of the 13th century. His contributions to the field of mathematics have left a lasting legacy that continues to be felt today. His book, Liber Abaci, introduced Hindu-Arabic numerals to Europe and presented a wide range of mathematical problems and solutions. This book was revolutionary at the time, as it replaced the cumbersome Roman numeral system with a more efficient and versatile numerical system. Fibonacci's work helped popularize the new number system and demonstrate its practical applications. The adoption of Hindu-Arabic numerals facilitated easier calculations and record-keeping, which had profound implications for trade, commerce, and scientific research. One of the most famous problems in Fibonacci's book is the rabbit problem. This seemingly simple problem involves the growth of a rabbit population under ideal conditions and has fascinated mathematicians for centuries. This problem, about the growth of a rabbit population, led to the discovery of the Fibonacci sequence. The sequence starts with 2 rabbits and grows exponentially, illustrating a pattern that is both simple and profound. In this sequence, each number is the sum of the 2 preceding numbers, like 1, 1, 2, 3, 5, 8, 13, and so on. This pattern not only has mathematical significance, but also appears in various aspects of nature and art. The Fibonacci sequence has numerous applications in mathematics and appears unexpectedly in various natural phenomena, from the arrangement of sunflower seeds to the spiral patterns in seashells. These natural occurrences of the sequence highlight the intrinsic beauty and order of the natural world. Beyond the Fibonacci sequence, his work had a significant impact on European mathematics. Fibonacci's methods and ideas were instrumental in advancing mathematical thought and education during the medieval period. He introduced methods for solving linear equations, calculating square roots, and dealing with fractions. These techniques were groundbreaking at the time and laid the foundation for many modern mathematical practices. These methods, presented in a clear and concise manner, were widely adopted by scholars and students alike. Fibonacci's work not only educated his contemporaries, but also paved the way for future generations of mathematicians, ensuring his legacy would endure through the ages.
Section 4. Geometry and the Renaissance Artist. Geometry played a crucial role in the Renaissance, particularly in the visual arts. Artists like Leonardo da Vinci and Albrecht Dürer embraced perspective, a technique that used geometric principles to create the illusion of depth and three-dimensionality on a two-dimensional surface. Perspective revolutionized painting, allowing artists to portray the world with unprecedented realism. The study of perspective required a deep understanding of geometry. Artists became mathematicians, studying the works of Euclid and other Greek geometers. They developed new techniques for representing objects in space, accurately depicting light, shadow, and perspective. The use of perspective transformed painting, sculpture, and architecture. The interplay between geometry and art was not limited to perspective. Artists also explored geometric principles in their compositions, using symmetry, proportion, and geometric shapes to create harmonious and aesthetically pleasing works of art. The Renaissance witnessed a fruitful exchange of ideas between mathematics and art, each discipline enriching and influencing the other. Section 5. Algebra's rise, unlocking the unknown. While geometry flourished during the Renaissance, algebra also underwent significant developments. Algebra, with its use of symbols to represent unknown quantities, provided mathematicians with a powerful tool for solving equations and exploring mathematical relationships. The 16th century witnessed breakthroughs in solving cubic and quartic equations, problems that had stumped mathematicians for centuries. Solving cubic equations involving unknowns raised to the third power proved to be a challenging problem. Mathematicians like Scipione del Ferro and Niccolò Tartaglia independently developed solutions, but their methods were initially kept secret. Later, Girolamo Cardano published a comprehensive treatise on algebra, Ars Magna, which included the solutions to both cubic and quartic equations, giving credit to Tartaglia for the cubic equation. The solution of cubic and quartic equations marked a turning point in algebra. It demonstrated the power of symbolic reasoning and led to the development of new algebraic techniques. These advancements paved the way for further progress in mathematics, including the development of analytic geometry and calculus.